Welcome to the course on power quality. We will discuss today the control techniques for DStatCom or distribution static compensator. I mean, this is the first custom power device on which we are going to apply these control technique. Of course, we will not like to repeat, of course, most of the compensating devices as well as the you can call it the even other active devices, we like to use these control technique. I mean, these can be modified and used for other compensators also. So, that is the reason we thought of we will discuss first for this for DStatCom, and then we will discuss only in little modification. So, this is the another control technique, I mean, which is used for this DStatCom. So, we call it like a instantaneous symmetrical component theory. In short, we call it IST based control algorithm. I mean, in this control algorithm, the product of instantaneous phase voltage for all three phase and the load currents of all the three give the instantaneous load power, and this instantaneous load power, of course, we consider that it consists of AC component that is responsible for harmonics, or you can call it like a negative sequence, and then we have a DC component which represents virtually you can call it fundamental active power consumed by the load. So, we can take it like a typically the average load power is extracted from the instantaneous power by passing through a low pass filter. So, we can get a fundamental active power consumed by the load. Well, this is the block diagram of this instantaneous symmetrical component theory based control. So, what we are doing, as you can see here, that we are taking a load current and the source voltage, I mean voltage at the point of common coupling, which we already got it for if it is a 3-wire system, 3-phase 3-wire system. So, we can sense only 2 line voltage, and from these 2 line voltage we can calculate the, we can estimate the 3-phase voltage, and which are used here. Of course, we already discussed earlier in some algorithm that those line voltage may be distorted or unbalanced. So, well, we have to, for avoiding the distortion, we have to pass them for band pass filter, so that only fundamental component of these voltage are achieved, and after that we convert them into the phase voltage. In these phase voltage we have to find out then only the positive sequence voltage, which are balanced set of voltage, and those we use. So, after from load current and the phase voltage, after multiplication of that we will give expression in that, we will get instantaneous power, and after low pass filter we will get the load power. Of course, if we have to maintain self supporting DC bus, we have to add here again the output of PI controller on the DC bus, I mean like, so that one can understand here. And another block is responsible for here for typical for getting the voltage amplitude from this voltage, and then we consider after low pass filter the amplitude of voltage, we take the amplitude of the voltage, and from passing through PI controller we consider this is the angle typically of the to be used in this typical control. So, this is we consider angle, because this angle will introduce certainly this reactive power required for the reference current like. And of course, we estimate the another quantity like A here, on which are calculated from VSA, VSP, VSC. And once we know this, I mean then these three expression of ISA, I mean VSA plus VSP minus VSC into the beta divided by A absolute and into PLDC, that give for really for A phase reference current of the grid. Then similarly, we calculate for B phase reference current and C phase reference current for the grid like. And once we have a reference current, we have a sense current of the grid on the grid side, and these error, I mean current error, we feed to PWM current controller, which we discussed. Either you can use the hysteresis current controller, or you can use typically the on off controller, or you can use the even a PI controller with the comparing the carrier wave to get the typically the switching signal for voltage source converter, which is used as a DStatCom, I mean in case of 3-phase 3-wire system like. So, this is the typically the explanation through the block, and these are the mathematical expression that we are from, as I already discussed, that we sense only 2 line voltage in 3-phase 3-wire system, and from that we calculate the 3-phase voltage by using this transformation. And once we got the phase voltage, we can calculate the amplitude here typically from this expression, the amplitude of the point of common coupling voltage. So, that is required of, we will discuss how we will get it. The average, then we estimate the average load power from the instantaneous active power, which is obtained from phase voltage and sense load current from this expression. This gives the DC and the AC, and the DC represents that consists of DC component as well as pulsating AC component, and DC component extracted by instantaneous power through low pass filter, which represents the fundamental active power consumed by the load, the real power which normally used for the considering the typically for doing the work in the system like or any load. So, a function beta is computed using a proportional integral controller on PCC voltage, and output of PCC voltage PI controller considered as a function beta, and this function beta is the proposed controller is used to keep the PCC voltage at constant magnitude, and this beta we can call it, which is on the voltage PI controller, where this is the point of common coupling voltage amplitude on which we put that, and this beta represents an angle, we can call it from this expression beta tan phi upon root 3, where phi is the phase difference between PCC voltage and fundamental voltage like. So, we can call it this function beta, it represents the how much phase shift you have to provide it typically for these in these reference current for the purpose of regulating the PCC voltage, because this may require your leading reactive power or lagging reactive power. So, that also taken into account as we discussed in the previous block diagram, and once we know this beta from here for voltage regulation, we can find out these three reference grid current, ISA star as a already in the block diagram we have discussed it about VSA plus VSA minus VSB into beta divided by A into PLDC, or similarly for B phase and similarly for C phase, where A is defined as a you can call it the VSA square plus VCB square VSC square like also. So, this gives us the 3 phase reference current, and comparing with the sense grid current, we have indirect current control for this D STATCOM. So, that explains this instantaneous reactive symmetrical component theory, which was devised in 1957 and used extensively in power network, either power system or other applications, even for machine electrical machine analysis. That is also used in the same way as we already talk about couple of theory for instantaneous reactive power theory as well as the DQ theory. So, this is another theory which is used for control of this typically of D STATCOM. Well, the another you can call it control, which is based on single phase PQ theory based control algorithm. Like it's interesting, it's a you can call it modification of your instantaneous reactive power theory used for normally typically single phase, how we can extend it to be used on 3 phase. For single phase you can use directly, but for 3 phase we have to modify for every phase. So, we can say that any single phase system can be analyzed as a 2 phase system by giving an pi by 2 lag or lead to the PCC voltage of that particular phase and current, and realized as a 3 independent 2 phase system, and the PCC voltage and current are considered as a quantity in alpha axis, where the pi by 2 lead voltage and current are considered as a beta axis. So, for each phase means let us say we have a 3 phase system. So, for each phase we will considering this alpha component as a original component, and the beta which is phase shifted by pi by 2 lead angle like also. So, this is typically the block diagram of single phase PQ theory based control algorithm for 3 phase D STATCOM. Here of course, we have again both the PI controller, we have a reference DC link voltage for the voltage source converter DC link, and then we have a feedback sense voltage on the DC link, which have a ripple also. So, that is why we have to use low pass filter to give a feedback, and this error we apply to PI controller, PI regulator, proportional integral regulator, and output of this we consider the P loss, that is the power loss we consider in the D STATCOM, and power loss consists virtually the interfacing inductor, ripple filter, you can call it dielectric loss in the DC link capacitors, and losses in the switching, you can call it devices like and diodes. So, all the losses virtually we equate it, because with the when we want to maintain DC link voltage, that much power have to be taken care by D STATCOM as a loss. So, that is the reason we consider the loss. And now, here what we consider it, this voltage, here we are transforming the 3 phase voltage. One is the directly we are taking this ABC voltage, directly we call it alpha beta component of for ABC 3 phase, and another all the 3 we take a 90-degree lead of this, maybe by some kind of compensator or some kind of filter which gives 90-degree phase shift. And similarly for current, we take a directly alpha component. For beta component, we take the directly 90-degree lead, like here, that is 90-degree lead, and all these we use in calculating the instantaneous active power for all 3 phases I mean which we are considered equivalent to 2 phase alpha beta, similarly for B phase, similarly for C phase, and similarly we take it for even a reactive power for all 3 phases for from alpha beta by cross coupling, I mean by using this expression. So, this gives the reactive power for all 3 phases A, B, C phase, and similarly reactive power for A, B, C phase, and of course, it consists of ripple. All these 6, let us say quantity consists the ripple, and and a DC component. DC component is corresponding to the fundamental active power and reactive power, which of course, we use the low pass filter. So, we get the DC component means, but I mean these can be different value, because the reason being that you might have unbalanced load. Similarly, for quadrature you can call it this even a reactive power also DC component can be also different, you might have a load unbalancing for all 3 phases. So, summing by all 3 and then divide by 3, we try to balance as a per phase. So, here in this per phase equivalent we add the loss, and then we get the total active power drawn from the supply for meeting the losses of the D STATCOM as well as the active power for required for the load. And here of course, we again have another PI controller. I mean we want to maintain PCC voltage. This is the reference for amplitude of PCC voltage, and this is the, you can call it the estimated voltage from PCC, the amplitude, and we again pass on this error to PI regulator, that is nothing but PI controller, proportional integral regulator, and output of this is a reactive power to be generated by D STATCOM. But out of this, the load reactive power have to be supplied locally, I mean by this D STATCOM to the load. So, we take a difference of this, and this is the reactive power which have to certainly have to flow into the grid to maintain the you can call it constant regulated voltage at the point of common coupling at the load point. I mean that may require little leading reactive power in general, or it may be lagging, depends on the typically the reactive power drawn by the load. And then from this, virtually from this active power and reactive power, we calculate the using the template which we already discussed in other technique. We get the instantaneous 3 phase active power for all 3 phases, and for reactive power all 3 phases, and when we add the both active and reactive power, we get the 3 phase reference current for the grid, and we have a sense grid current which we compare it and in the current controller and give the getting signal. So, we already discussed this is indirect current control, and we get the getting signal for the inverter which is used, voltage source inverter is used for as a D STATCOM, I mean like for the compensation. So, this is the, we call it single phase PQ theory, because we are using alpha beta component for each phase. So, alpha beta transformation, that called Clark transformation, is used only for instantaneous reactive power theory. So, this is modified for per phase basis, and we apply for all 3 phases independently, and then of course, we take together and then get the compensation from this also. Well, these are the typical expression for this PQ theory, alpha beta quantity of phase voltage and current. I mean these are the alpha component and these are the beta component which are 90° phase shifted. Similarly, alpha component of load current and beta component of load current. And once we have all 6 quantity, then we can calculate the power, active power for instantaneous active power for all 3 phases separately, and reactive power also for 3 phases separately. And once we have all these 3, then we pass on this through low pass filter. And instantaneous active power of 3 phases consists of DC component and oscillating AC component, and the average active power are extracted from instantaneous power using low pass filter, which we discussed in the block diagram. And to achieve the balance active and reactive power demand for all 3 phases, the average of single phase active power is taken as a as well as for reactive power. So, you can have a addition of this divide by this, so that you get per phase basis this active power typically for load balancing. Similarly, the reactive power we take all sum divide by 3, because these 3 can be unequal depending on the unbalanced load, as well as you can have a even the different reactive power in the different phases of the typically of the drawn by the load like. So, that explain, and you can have a per phase, you can have a again here the power plus the loss which is on DC link voltage controller, and this is the reactive power of the load, and this is the output of PI controller for regulating the reactive power generated by the D STATCOM, which we calculate from voltage PI controller, and this is the voltage error, and this is DC link voltage error, this is the loss power component which we add here. So, once we know these, of course, we can find out from these relation of P and Q, we can find out the instantaneous active power, instantaneous reference grid current by both power and active power and reactive power by using this expression, and this expression is the same as the instantaneous symmetrical component theory we discussed already earlier, we call it IRPT. So, this gives a 3 phase reference current which we compare it with the sense grid current for indirect current control, and we give the throw those current errors depending upon whether we use hysteresis current controller or we use typically the, you can call it like a even any other PI current controller, we get the gating signal from those reference and feedback currents like so. So, that is about single phase PQ theory. Similarly, a DQ theory is also modified to apply, single phase DQ theory also modified to be applied for 3 phase D STATCOM, and this is about the typical explanation for that. So, it is simple to design controller for 3 phase systems in synchronously rotating DQ frame, because all the varying signal of system become DC quantity and time variant. That is the advantage of this DQ theory. And in case of 3 phase system, initially 3 phase voltage and current signal in ABC are transformed stationary alpha beta and then to synchronously rotating DQ reference frame. However, to transform a signal into stationary alpha beta frame, at least 2 phases are needed. Hence, a pseudo second phase for the arbitrary signal is created by giving a 90-degree lag to the original signal, and the original signal represents alpha axis and 90-degree signal typically beta axis component of stationary reference frame. So, here of course, we use this both the transformation, and this is the typically the block diagram of this, you can call it single phase DQ theory. So, here what of course, here also we have a what we discussed already, the typically the DC link voltage control of through PI, and of course, we give 1/3 here because we divide for all 3 phases, the losses have to, and similarly the voltage regulation for the point of common coupling, this also we divide by 3. Now, what we are doing here, if you look into carefully, and we are having a typically the 3 phase sense voltage, and from these sense voltage we are getting a sin theta cosine theta, because that is required for typically you can call it for either you get PLL from or from template, this sin theta cosine theta required for DQ transformation. So, we get from this voltage only, and now in current we are having a original current for A phase and 90-degree shifted current, and that give us alpha beta, and using sin theta cosine theta which are generated from the voltage of point of common coupling, we get the typically you can call it IL AD and IL AQ. Similarly, we do for B phase, we have a B phase current as alpha original and then the 90-degree shifted another for B phase as a beta component, and again DQ transformation. Similarly, for C phase DQ transformation, and all 3 D axis current we add here and Q axis current we add here, and after adding this we use the low pass filter. So, we get the DC component or fundamental component of it, and then we divide by 3 because we have to convert per phase basis, add with the loss here. So, we get the amplitude of active component current, and here we get the, we have again we subtract here because this have to met from D STATCOM locally the reactive power, and the remaining should flow only to the current. So, we get the amplitude of reactive current of the grid, and we have again sin theta cosine theta because these are the DC quantity, or you can call it in you can call it DQ reference frame, and using cosine theta sin theta we convert into typically you can call it in again back into DQ to alpha beta, or you can call it all 3 A phase, B phase and C phase current. So, we have a 3 phase current, you can call it here reference current, and by sensing the load typically the grid current, we can just compare and use the current controller for generating the gating signal for D STATCOM. So, this we call it the single phase DQ theory like or so. Well, single phase, the as far as mathematical formulation of single phase DQ theory based control algorithm, we have a, again we are sensing for 3 wire system the 2 line voltage, and we are estimating 3 phase voltage from here from this expression as we did in other control algorithm, and we have a amplitude calculation of the phase voltage, and we calculate then typically the template which we are considering, and from these template virtually we are considering these are the cosine function, and from this coordinate template we are getting sine function that does not require any PLL and very sophisticated. So, we get very straightforward the simple calculation from that like also for cosine theta sin theta. So, considering the one of the phases of 3 phases at a time, and then transform the voltage and current to that particular phase into alpha beta reference frame. So, we have a 3 typically the 3 voltage, and then we are transforming these 3 voltage 90-degree phase shifted. Similarly, we have a 3 phase load current, and we transform the 3 phase load current to 90-degree phase shifted, as we already discussed in the block diagram. So, once we have the two sets of current for all three phases, I mean by using this cos theta sin theta transformation for A phase, B phase separately and C phase separately, we get the dq component, you can call it for load A phase current, B phase current and C phase current like. And then I mean from that d axis component of load current of all phases are added together to obtain the equivalent d axis current, and similarly q axis component of load current of all three phases are added equivalent to. So, we have a here all three we are adding, and even a quadrature component of load current or reactive current also we are adding. And from this of course, I mean once we add, it has a DC component, AC component. A DC component is for active power of the load, and AC component is corresponding to, you can call it like a ripple is corresponding to either negative sequence or harmonics and other thing, I mean like component. Similarly, for q axis, this is fundamental reactive current of the load equivalent, and the DC component can be extracted by filtering the equivalent D and q axis component using the low pass filter here, as we have discussed in the block diagram. So, after getting this DC component, we can get a amplitude of per phase basis of your active component, that is the load component plus the loss component for the STATCOM, and we divide by 3 because this loss also have to be supplied by all three phases. Similarly, we take a typically for Q, I mean like quadrature also, the reactive power generated by STATCOM by PI controller, as we are calculating here by PI controller on the voltage PCC voltage amplitude. So, that minus the we are taking like the reactive power required by the load, and then because that have to be supplied locally by the STATCOM. So, divided by 3 means we are getting per phase, and this is certainly the active power loss equivalent component by losses in the STATCOM, which are on DC, I mean achieved by putting a PI controller on DC link voltage. So, these are the two amplitude for active power and reactive power component of current from drawn from the supply system. Now, from getting this D and Q component, I mean using this transformation for we can get it typically for A phase, B phase and C phase, three phase reference current for the supply or grid current, or we can call it source current, and we have a sense source current. So, we compare them and get the current controller on that, and we get the switching signal corresponding to that like also. So, this gives the typically this control algorithm. Well, typically another algorithm, just to give you an idea, like a neural network, I mean people are using this neural network concept typically in many applications. So, here also we also given the simplest neural network algorithm, we call it least mean LMS, means least mean square, and a line based control algorithm for the control of this STATCOM, and I consider this is one of the simplest among the all control algorithm which we have discussed so far. So, just here you can just see even a single expression is responsible for extracting the fundamental active component from the load current. So, we have here again the DC bus voltage controller PI controller, which we are estimating. We have a reference DC link voltage, we have feedback DC link voltage, and we are using the PI controller, proportional integral controller, regulating the DC link voltage. Of course, this is the after the low pass filter after sensing this, and this gives us the loss component which we just take into this block. And then of course, we given a weight back to the input to this, and we are giving here as a input as a load current, and you can see as a input as a load current, we are giving a I mean for typically for A phase, and we are giving a template which we are calculating template from point of common coupling voltage, phase voltage we are calculating phase template, and we are taking a quadrature template. So, from phase template also we give it the previous weight, the total weight, and we take a load current and the template, and from using this single expression we are able to extract the weight corresponding to, you can call it the active component of for A phase current, and we are able to estimate virtually A phase even a typical current here also. Similarly, for B phase active component, similarly C phase active component, and this is reactive component for only one expression for, you can call it extracting, and this is for B phase reactive power and C phase reactive power. So, we have a reactive power component, we have active component, and this active power component we add by 1/3, and here also we take all three. So, we get this weight, and once we get this total weight, we get the reference current here, and this we take here for A phase, reactive component we take from this phase to here, and we get the total component for grid for voltage regulation as well as for power factor correction. Of course, if you do not want typically the you want only power factor correction, then typically I mean you can just keep this component here the 0, I mean the reactive component, and that can give you power factor correction. So, similarly for B phase and C phase, and you are getting 3 phase grid reference grid current, you have a sense grid current, and you have a current controller here, current control for the voltage source converter operating as a VSI. So, this is one of the simplest, you can call it the single expression is able to take the fundamental component of the load current of A phase, B phase and C phase very effectively, and we are able to balance per phase basis also by calculating from this slide. And this is the mathematical, of course, equations correspond to that. So, from line voltage we get the phase voltage, we get the amplitude of voltage, and we get template here as a cosine theta for all three phases from this amplitude and instantaneous, and we get the quadrature component, and then we get typically here even the quadrature sin theta cosine theta, and then we get this active weight, I mean which we have already given expression for A phase. I mean this is A phase load current, we have a template here and the template there. So, using just this simple expression, I mean here it is a one convergence factor, this is becomes very important, this eta convergence factor. I mean if you keep very high, filtering will be poor, if you keep smaller then it will be slower convergence. So, you have to make a compromise, and we found 0.2, I mean typically 0.2 value of this convergence factor have been quite good a compromise, but of course depends on, I mean this can be further looked into as adaptive also, even some of our students have used this as adaptive manner also to during dynamics and during steady state you can modify also. And similarly, we get the weight corresponding to quadrature component of all three phase load current from using this expression. So, all these 6 weight for active and reactive component of load current, we are able to extract the fundamental active and reactive current from the load current line. And that of course, I mean we have a loss again from PI controller here, and we have a typically the all three active component of current, fundamental active component of current. They may be unequal because of unbalanced load, but here by taking 3 we are calculating per phase basis. Similarly, reactive power generated by D STATCOM minus the reactive power consumed by the load for all three phases and then per phase basis, where the loss component we calculate from PI controller again on DC link voltage as we did in other control algorithm, and similarly the voltage regulation at the point of common coupling regulating the amplitude of the voltage like common. So, that gives the basically the amplitude of active component and reactive component of the supply current, and then from this we can calculate for all three phases using this weight multiplied the template for A phase, B phase, C phase, the you can call it the active component of all three phase grid current, similarly reactive component of the grid current which is required for voltage regulation, but you can keep this as a 0, then WQ 0, then you will get a power factor correction only by this, and then you can add all both the component of for A phase, B phase, C phase getting a, you can call it the reference total reference grid current, and by comparing it with the sense grid current, I mean we can generate the getting signal for the 3 phase voltage source converter operating as a D STATCOM like also. So, that control, I mean these we have discussed enough number of control algorithm for D STATCOM, and these control algorithm of course we will be covering the lot of active compensator. This was the shunt, then we will talk about the even a series compensator, then hybrid compensator, then we will go even later on other cases also like a active filters. So, we will not discuss it again, we will just discuss the modification. So, at one place we wanted we should discuss all these control algorithm in a warm form, so that you understand, and then the little modification we will discuss it. Now, we will like to of course discuss that these control, I mean after this control algorithm we look into a case study of these D STATCOM 3 phase 3 wire by modeling the complete system through including the control and power circuit and load modeling also, and even the different kind of disturbances which you can think about demonstrating like a load unbalancing other thing. So, and then simulated through that MATLAB modeling. Of course, you can model in any other form. Earlier we were modeling not through MATLAB, we were just making our you can call it the program code and then simulating the performance. But now such software like MATLAB are available, so you can develop the total model itself from the block for this complete system including the control algorithm, and then we are able to get a performance of this D STATCOM like So, this is a typical case study, I mean performance of you can call it synchronous reference frame control 3 lag voltage source converter based D STATCOM for 0 voltage regulation mode at varying load. So, you can just see it is a 3 phase PCC voltage, it is 3 phase grid current which are balanced current, but of course, they may not be in phase because you are using for voltage regulation, okay, maybe slightly leading, and this is the load current. You can see the load current here we have a 3 phase load current lagging power factor load current, but here we have removed one phase in 3 wire system. So, 2 current 1 return, it is like a single phase, one current is going and returning. So, this is load unbalancing to demonstrate, and again back putting that load current back, I mean so that I mean you look into how the dynamic response is there, and this is the compensator or D-STATCOM current. So, D-STATCOM current, if load is unbalanced, the D-STATCOM current also become unbalanced. Otherwise, here it was only compensating the reactive power, because these were lagging load, and you have to maintain the voltage. So, these are compensator current for all three phases, and this is the voltage. You can see the regulated voltage across the point of common coupling. Of course, during dynamics it takes time because of action of PI control, but it remains regulated. And this is the DC link voltage, because when you remove the load, certainly there will be a slight overshoot in the DC link voltage, but with the time it gets settled down, and again when you apply the load there will be some undershoot, but that comes within the design limit, and you are able to get a quite satisfactory performance as far as the grid current are concerned. Even the load is unbalanced, but grid current are balanced and sinusoidal throughout the operation in this 0 voltage regulation mode. Then the next mode is, of course, is unity power factor mode. Unity power factor mode, we discussed it earlier. So, these are the point of common coupling voltage, and these are the unity power factor current, balance current, sinusoidal current, current in phase with the PCC voltage. And when load is removed, you can just see how the current are modified. One phase load is removed. So, load is a load balancing. So, it provides the reactive power compensation as well as the load balancing, and you can see the compensator current. So, these are the some current, because it is a lagging power factor load. So, it provides the leading current by the compensator, so that power factor is unity of the grid current. And here you can see the unbalanced current, because the load is unbalanced. So, compensator have to generate unbalanced current, so that the grid current are balanced current, and again back putting the load it comes that. And you can see here we are not regulating the voltage of typically of point of common coupling. So, when you have a load, certainly the voltage at the point of coupling reduces from the supply voltage, and of course, when you remove the load it comes closer to that, but still some small difference. Similarly, when you apply the load back, it goes little down, but you can see the DC link voltage when you remove the part of the load, where you are drawing the more energy even for fitting the load. Now, same energy gone coming for some period, and that gives the overshoot in DC link voltage for short period, but after the controller action it comes back to the same. And similarly, when you apply the load back, it goes to undershoot, and after the action of PI controller recover back. So, you can just see this overshoot undershoot is hardly, goes typically 4 to 5%. It depends on your controller parameters, on PI controller regulator parameters, how it can be made fast. But if you want to really avoid this, you can use another, you can call it the controller like a sliding mode controller also, which may give better performance than PI controller. But here we are just discussing kind of a one of the benchmark as a case study like. Well, that was the typically for 3-wire system. Here we have a 4-wire system. We are using a performance of whole leg 4-wire system, voltage source converter, D-STATCOM for load balancing and power factor correction mode. So, you can clearly see here it is a 3-phase supply current, 3-phase supply voltage, 3-phase grid current, and here it is the load current. So, you can say load is connected between line to neutral for all 3 phases, and during this duration 2-phase loads are there, but 3rd phase load is removed here, and because of this you will find there will be a kind of load neutral current. When there was a balanced load current, there was no neutral current was there, but load is unbalanced. It means now 2-phase line to neutral, there is a load connected. So, 1 phase is not there, that is why you have a load neutral current appearing there, and again you recover back. So, again neutral current goes 0. But during this period when you have a load unbalancing, of course, 1 phase load is less, so power drawn is less. That is why the total balance current drawn from the supply is also reducing here. And the compensator, of course, 3 legs are generating the current for balancing this, and so that supply current are balanced, and the 4th leg is compensating the neutral current, so that grid neutral current is maintained 0. So, these are two opposite, whatever the load current is there, the compensator neutral current is just exactly opposite and same magnitude, so that the neutral current is kept 0, and the DC link voltage remains regulated here, because it is a power factor correction. So, we have not shown the voltage waveform. So, that is demonstrative in 3-phase 4-wire system. Typically neutral current compensation also along with the reactive power and load balancing like this is the another case study again of you can call it like a 4-wire 4-leg voltage source converter based D-STATCOM for load balancing and 0 voltage regulation. So, you can clearly see here it is typically the voltage at the point common coupling is regulated, which we will see in PI controller, and these are the grid current which are balanced, but of course, may be slightly leading because you have a lagging power factor load, and here we remove the load of 1 phase and apply back. So, you will see neutral current here it is 0, and once the load unbalancing is there, neutral current appears, and the compensator 3-phase current and neutral current of the 4th leg of compensator, they are able to compensate for neutral current as well as the reactive power, as well as you can call it even for regulating the voltage. And you can see here neutral current is 0 throughout, and point of common coupling voltage is also regulated, and DC link voltage also remains regulated also. So, it depends on control of parameter also. So, that is another typical case study what we have looked into. The another case study for three single phase, 4 wire system, you can use the 3 single phase voltage source converter also, the STATCOM for load balancing and voltage regulation. And here you can say the 3 phase PCC voltage, then you have a 3 phase grid current, and which are balanced and sinusoidal at unity power factor. And here you can say load is unbalanced, and having a load unbalanced from 3 single phase, you are providing the compensating current here, and you are providing the load neutral current here. So, you are putting the compensator current through typically through the neutral just exactly opposite out of phase, so that neutral current in the grid is 0, almost negligible. And this is the DC link voltage of this. Why DC link voltage? You can see little enlarged, because this is lower voltage, you are able to see the second harmonics when there is unbalancing of the load. That is the nature, because we are using 3 single phase here. So, you have a slight overshoot when you remove the load, because energy is coming, and when you apply again back the same load, then slightly undershoot is there. But second harmonics certainly will be there, which I have discussed many times when we were using low pass filter for regulating the DC link voltage of the STATCOM. And then the same compensator for 3 single phase voltage based STATCOM for wire compensation for load balancing and 0 voltage regulation. So, here what we are having like a 3 phase PCC voltage, then we have a grid current which are balanced and sinusoidal, and here is a load is made unbalanced, and compensator accordingly compensates, so that grid current are balanced. It is a neutral current of the load and compensator neutral current, which compensate this exactly out of the phase and same magnitude. So, that neutral current is almost, source neutral current is almost negligible, and the point of common coupling voltage you can see clearly remains regulated throughout the operation, like whether load is less or load is unbalanced. And here you can see the DC link voltage again have apart from that your second harmonics during load unbalancing, and then slight overshoot, undershoot, and removal of the load and application of the load, also, because it gives a instantaneous energy comes back to the DC link, and here it takes a instantaneous energy from the DC link capacitors of the STATCOM. So, with this, these are the case studies we discuss it typically the for voltage regulation power factor correction for 3 wire system and 4 wire system. Now, we will like to discuss typically some of the, you can call it numerical examples on these STATCOM starting from single phase, 3 phase 3 wire, 3 phase 4 wire STATCOM system for used for compensation. So, this is the first example, a single phase load Z equal to 2.5 per unit plus J 1.25 per unit has an input AC voltage of 220 volt 50 hertz AC supply and base impedance of 9.15 ohm per phase, and it to be realized as a unity power factor load on AC supply system using PWM based STATCOM. Calculate the value of compensator current, its VA rating, supply current, equivalent resistance of compensated load. So, you can clearly see here we have a supply and we have a load which is a inductive load, and we have a STATCOM typically circuit here. So, what we have to find out for a given load, we have to find out this compensator current, so that we have a unity power factor on the supply side. So, after getting typically the design and we just simulated with power control, you can clearly see the grid current is in phase with the grid voltage, and this is the load current which is little lagging power factor, and this is the, you can call it like a compensator current, and this is a DC link voltage. It is slightly enlarged, but you can see in single phase this will be second harmonics, that is the nature of the system, second harmonics will be there. So, over this voltage of your whatever you are regulating, you have a second harmonics reflected on the DC link of this like. Coming to the solution part of this, given that the supply voltage is 220 volt, frequency of supply 50 hertz and single phase load equal to Z equal to 2.5 plus J 1.25 per unit with a base impedance of 9.15 ohms per phase. So, load resistance comes to be, after calculating it, comes 22.875 ohm, and load reactance comes for 11.44 ohm, and the load impedance comes 25.575 ohm, and the load current before the compensation comes V upon Z, it comes typically 8.6 ampere, and compensator current which is for reactive current I s old into sin theta, I s old x upon Z, putting the value it comes 3.847 ampere, and the VA rating of the compensator is V into IC, that comes 220 into 3.847, that comes 846.34 VA, and supply current after the compensation is typically IS nu equal to IS old cos theta, that is IS old into R upon Z. So, it comes typically 7.692 ampere, and equivalent resistance of compensated load is R equal to V upon typically V upon I. So, it becomes 220 upon 7.69. So, it comes 28.6 ohm. So, taking another example, a single phase AC supply has AC mains voltage of 230 at 50 hertz and a feeder source impedance of 1 ohm, resistance here and the 3 ohm inductive reactance, after which a load of 16.J12 ohm is connected. To calculate the voltage drop across the source impedance and the voltage across the load, epilogue based D STATCOM is used to raise the voltage same as 230, which was the grid voltage. Calculate the voltage rating of the D STATCOM, VA rating of compensator and current rating of the compensator. So, after getting proper design and control, these are the waveform after the simulation with proper control here, and you can see clearly supply voltage and supply current, they are typically here, and supply current typically supposed to be slightly leading than, and this is the load current, and this is the typically compensator current, or you can call it like the current draw put from this, and this is the DC link voltage, which certainly takes a second harmonics into it like so. Well, so given that the supply voltage Vs 230 volt, frequency of 50 hertz and single phase load of 16.12 ohm and feeder impedance of 1 ohms resistance and 3 ohm reactance. So, total load resistance of 16 ohm and load reactance 12 ohm. So, admittance of load admittance, and we can get the active power from conductance V square GL. So, this is the active power consumed by the load, and this is the reactive power consumed by the load, and the total impedance we can find out it, including the source impedance here with this relation, and we can find out the load current before the compensation Vs by total load total impedance of the circuit, and then we can find out the voltage drop across the from that source impedance multiplied the current, that is the voltage drop across the source impedance before the compensation, and the voltage across the load we can find out. So, that is the you can call it the current drawn from the source multiplied the load impedance. So, it comes to 202.88 in place of your typically of 230 volt. So, that voltage you can say it reduces because of source impedance and lagging power factor load, which give you worst voltage regulation. Now, we want that the compensator should regulate the same voltage at the point of common coupling at the source voltage, that is 230 volt. So, V rating of compensator we can call it for VL equal to Vs, that will be QC equal to Q minus QL. So, QL can be calculated from the following equation. We have here the equation, quadratic equation for this AQ square plus BQ plus C, where you can call it Q is calculated from this relation, where A is, B is here and C is here, and once calculating the ABC, and we get the Q equal to typically 870 VA, and total compensator current, that is for voltage regulation only, and we can get typically here QC equal to Q plus QL, and both are of course of you can call it leading nature. So, we get minus 2457, that minus means it is a leading reactive power, had become 2.457 kVR, and the equivalent current rating of the compensator will be the VA rating, VR rating divided by voltage. So, this is the current rating of the compensator like also. I would like to discuss on this distribution static compensator virtually on the applications and then typically related to the problem. So, a 3-phase 3-wire D STATCOM is employed at 415 volt 50 hertz system to use to provide reactive power compensation at for unity power factor of 3-phase delta connected 15 kilowatt induction motor operating at 0.8 lagging power factor. So, calculate the line current, equivalent per phase resistance, the compensated load, D STATCOM current, its kV rating and interfacing inductance, DC bus capacitance for this D STATCOM, where the switching frequency is 2.5 kilohertz and DC link voltage is 700 volt, and it has to be controlled within 5% range, and the ripple current in the inductor is 12% like. So, this is the typical circuit, like the induction motor is connected to the grid, but with this D STATCOM we want to have a power factor on the grid side. It means all the reactive power which is required by the induction motor load is to be supplied by D STATCOM, and these are the typical you can call it the all the currents voltage and current of this circuit, including the DC link voltage also. So, coming to the solution, that given that Vs equal to 415 by root 3 per phase voltage 239.6, frequency 50 hertz, a 3 phase delta connected 15 kilowatt, induction motor operating at 0.8 lagging power factor, the switching frequency 2.5 kilohertz and DC bus voltage is 700 volt with a 5% range and ripple current in the inductor is 12%, modulation index is 1 and DC VDC of STATCOM is 700 volt, A equal to 1.2 and frequency of switching 2.5 kilohertz. So, we can calculate the ripple current, I mean 12%, that is 0.12 into the current of the typically of how much is the D STATCOM. So, 15.61, so it comes 1.87 and we know minimum DC link voltage is provided 5% less than 700, so it becomes 665 and we can find out the current virtually for, I mean like typically corresponding to the load, that is 15 kilowatt divided by power factor 0.8 415 root 3, so it comes 26.085. So, the supply current after the compensation is I s nu equal to I s old cos theta and that is 26.08 into 0.8. So, the load current active component current is 20.868 ampere and the equivalent resistance of the compensator load is V upon I. So, that is per phase voltage 239.6 divided by per phase current 20.868. So, it comes 11.482 ohm and the D STATCOM rating is corresponding to the reactive power required for the load, that is I d estimate. So, I s sin theta I s or under root 1 P f square. So, it comes like 26.08 into 0.6 and it comes 15.651 ampere and the V rating will be 3 into phase voltage into the current of the D STATCOM. So, it comes 3 into 39.6 and 15.61, that comes 11.25, that is the kV rating of the D STATCOM. And from this we can calculate the interfacing inductance, I mean which require LST with this standard formula which we derived earlier, root 3 by 2 into MA VST upon 6 Fs into del S. So, that comes 17.92 millihenry and the DC bus capacitance of D STATCOM is computed from the stored energy dynamics as delta equal to half C V num square and from this we get the capacitance value typically of 4709.55. Considering that we will recover this energy in 10 millisecond like also. Well, coming to another fourth example of D STATCOM, a 3 phase 3 wire D STATCOM is applied at 415 or 50 hertz system to use to provide the load balancing and power factor correction of single phase 25 kVA unity power factor load across the two lines, calculate the line current, D STATCOM current and kVA rating. This is how it is a single phase load line to line connected and we have a D STATCOM connected across this. So, D STATCOM provide the load balancing and unity power factor on the grid side and these are typical waveform of supply voltage PCC voltage and the grid current which are balanced and sinusoidal at unity power factor and these are typically the load current across the two like and third phase do not have a load because it is open circuit and then these are the compensator current and DC link voltage like. So, coming to the solution, given that in a 3 phase 3 wire supply RMS voltage 415 by root 3 239.6 and frequency 50 hertz and active power of load is 25 kilowatt at unity power factor. So, the load current in AB line to be before the compensation is ILAB equal to ILBA, that is P upon V into PF. So, it comes 25,000 divided by 450, so it comes 60.24 ampere and single phase load connected across line to line to be realized as a balanced load on the 3 phase supply and 3 phase 3 wire D STATCOM is used for this purpose, which balances this load through circulating the current in AC side, considering the load connected across AB line in 3 phase ABC system. So, load impedance we have calculated V square by SL. So, that is 415 square by 25,000 and comes the load resistance virtually of 6.889 ohm. Now, once we know the load impedance, we can find out the typically the current going into the line, that is voltage 415 at 30 degree angle divided by 6.89. So, it comes 60.241 at the angle of 30. Similarly, the current other two will be of 60 same amount of current 60.241 ampere and the supply line current will be all three equal. It will be P upon 3 Vs, that is 25,000 into, because that is total power now distributed on 3 line. So, 3 into 30 and this comes the line typically the grid current becomes 34.78 ampere like. And the 3 phase D STATCOM current we can find out from those relation, I mean from load current minus the supply current, that will be compensator current we can keep the value, it comes 34.78 ampere, then other also 38 and 30.7 ampere, of course at different angle correspondingly. And V rating of this we can calculate typically from all typically phase voltage multiply the respective current adding together. So, it comes around typically it comes 25 kVA or so. So, this example give you the typical example of load balancing, as well as it have a unity power factor on supply side, in spite it was single phase load connected across unit power factor line to line, which is very common load, like maybe a traction, maybe furnaces, plenty of load may be of this nature of quite high rating, which can be probably can be designed in the same manner the D-STATCOM for those applications. Like coming to another example, a 3-phase 3-wire D-STATCOM applied at a 415 volt 50 Hz system to provide load balancing and reactive power compensation for unity power factor of single phase load of 75 kVA at 0.8 lagging power factor load across two lines as shown in figure. Calculate the supply line current, D-STATCOM current and kVA current. So, this is just typically 0.8 lagging power factor load, I mean that is across line to line, third line is open, but by D-STATCOM, keeping a D-STATCOM current, we can have all three line current on the grid side balance and sinusoidal and corresponding waveform after making the control, and these are the 3 phase voltage, then 3 line load current, third phase of line do not have a current, these are compensated current and DC link voltage. So, now coming to the solution part of it, a 3-phase 3-wire D-STATCOM is applied at a 415 volt 50 Hz system to provide load balancing and reactive power compensation for unity power factor of single phase 75 kVA 0.8 lagging power factor load across two line as shown figure. Calculate the supply current, D-STATCOM current and kVA rating. So, given that supply voltage of 415 by root 3 to 39.6 volt, frequency of 50 Hz and active power of single phase load equal to 75 at 0.8 lagging power factor, the load impedance is ZL equal to V square S upon SL. So, it comes 2.2696 ohm and at the angle of 36.87 degree. So, the load current will be here 415 by root 3, 415 at the angle of 30 degree divided by the impedance of the load 2.296 at the angle of 36.87. So, current comes typically 180.722 ampere at the angle of minus 6.87 degree, and of course, for line B it will be just minus of the value of this. So, coming to this single phase load connected across line to line is to be realized as a balanced load on the 3-phase supply. A 3-phase 3-wire D-STATCOM is used for this purpose, which balances this load by circulating the current on AC side. Let the load is connected across line AB and 3-phase system, and supply line current will be ISA equal to ISB equal to ISC equal to IS, and that will be your SL upon 3 Vs. So, that will be putting the value of your 75 into 0.8. So, that comes 83.47 ampere. All three lines have a same value of current and it is realized as a 3-phase balanced unity power factor load, and D-STATCOM current will be your ICA will be ILA minus ISA, and keeping the value it comes 98.35 ampere at the angle of 12.66 degree. Similarly, for line ICB will be ILB minus ISB. So, it comes typically after the keeping the value it comes 166.663 ampere at the angle of 145.706 ampere, and ICC ILC minus ISC. So, that comes typically because there is no load on this. So, it becomes minus of supply current only. So, it becomes minus 83.47 ampere at the angle of 120 degree or so. So, and the V rating of the D-STATCOM will be your S equal to the voltage multiplied the current. So, it comes typically 83.497 kVA. Well, coming to another example, a 3-phase unbalanced delta connected load ZAB equal to 9.9 plus J1 per unit and ZBC 5.5 plus J2 7.5 per unit and ZCA 3.5 plus J1.5 per unit has input line voltage of 15 volt 50 Hz and AC supply base impedance of 9.15 per phase. So, it is to be realized as a balanced unity power factor load on 3-phase supply system using PWM based D-STATCOM. Calculate the supply line current in ampere, D-STATCOM current in ampere and kV rating in D-STATCOM and equivalent resistance per phase of compensated load. So, these are typically a unbalanced delta connected load. We have a D-STATCOM, and purpose of D-STATCOM is to provide the load balancing as well as for correction of power factor. So, that supply side we have a unity power factor balance supply current here, and you can see after the design keeping the value and then with the power control, these are the waveform of 3-phase grid current, then 3-phase voltage, 3-phase grid current, then 3-phase load current which are unbalanced, and then 3-phase compensator current with the DC link voltage. Coming to the solution, from that, given that supply voltage 415 and frequency 50 Hz, 3-phase 3-wire unbalanced data connected load with the impedance of ZAB 9.0 plus J1 per unit and ZB 5.5 plus J2.75 per unit, and the ZC a 3.5 1 plus J 1.5 per unit with the base impedance of 9.15 ohms per phase. So, we can find out per phase voltage 415 by root 3 into 239.6, and we can find out the impedance, actual impedance multiplying the base impedance to per unit impedance. So, for AB it comes 82.39 plus J 9.15, and for BC it comes like 50.325 plus J 25.125 ohm, and ZC it comes 32.025 plus J 13.725 ohm, and load admittance with that is 1 upon YAB is 1 upon ZBA. So, we get the typical value, and the load phase we can call it the load phase current, that is the voltage line voltage multiplied the admittance of the load. So, that is the line voltage 415 at the root 3 because that is the line voltage, and that is the admittance of the load. So, it comes 5.006 at the angle of 23.6, and similarly for load line BC and load CA we can typically find out admittance this, and it comes 7.337 at the angle of minus 116.57 degree, and similarly for line CA it comes 11.191 at the angle of minus 233.2 degree ampere. Well, we can calculate once we know all the conductance. So, we can find out the total active power consumed by the load, that is PT square VA square GAB, because all conductance or substance in parallel. So, we can take only active power. Similarly, for B phase, C phase, and if we calculate all and sum it, it comes typically 9.35 kilowatt, and per phase active power will be by 3. So, it will be just by 3 of it. So, it will be 3116.7 watt, and the supply current we can find out after compensation will be VT by per phase voltage, putting all this. So, it comes like it will be 13 ampere at the rate angle 0, similarly minus 120 degree, 13 at the minus 120 degree ampere, and for phase C it will be 13 plus 120 degree ampere. So, now we can find out 3-phase D STATCOM current, that is the load current minus the supply current for A phase, and it comes 5.06. Similarly, we can find out typically for CB, and it comes typically after calculation 2.99 at the angle of 117.57. Similarly, for CC, that ILC minus IC we can keep the value, and then it comes 5.56 at the angle of 61.33 degree ampere like. So, that gives the compensator current. Now, we can find out the kVA VA rating of the compensator, that voltage multiplied the all sum of the 3 currents, per phase voltage 239.6, and the current of all 3 it comes 3.8775 kVA, and equivalent delta connected resistance. You can find out from power 3 V square by PT, and we have here the resistance connected 5.277 ohm. So, this gives you unbalanced a non-resistive load makes the balancing as well as for perfect correction. Coming to another example of now 3-phase 4-wire unbalanced load having a ZA equal to 3.0 plus J 2.0 per unit connected across the phase A and neutral terminal is fed from AC mains with the input line voltage of 415 50 Hz and a base impedance of 9.15 ohm per phase as shown in the figure. It is to be realized as a balanced unity power factor load on the 3-phase supply system using 4 lag pendulum based D STATCOM to calculate the supply line current, D STATCOM line current, its neutral current, kVA rating and equivalent per phase resistance after the compensation, because the compensation provide the neutral current compensation as well as balancing the load and unity power factor on the 3 line. So, these are typically 4 lag compensator we are using, and the load is connected between one phase and line, the lagging power factor load. So, very purpose of D STATCOM is to provide the let us say neutral current 0 and all 3 currents equal, balance and unity power factor. So, after designing and with the power control, you can find the 3-phase voltage, 3-phase balance current at unity power factor, then you have a load current, then you have a compensator current and load neutral current and compensator neutral current, and you can see your source neutral current is made 0 because the load neutral current is compensated by 4th lag of voltage source converter, and the DC link voltage is regulated to 700 volt according to the design. So, coming to the solution of it, giving supply voltage of 415 by root 3, that is 239.6 and frequency of 50 hertz and single phase loading 3.0 plus j 2 per unit connected between phase and neutral terminal with the base impedance of this. So, if we want to get exact impedance, so we can multiply this per unit multiplied the base impedance, and the impedance comes to be typically of 32.99 at the angle of 33.69, and the load current before compensation ILA can be 239, that is the phase voltage between line to neutral divided by the impedance. So, it comes 7.26 at the angle minus 33.69 ampere. So, total active power, I mean we can find out I square RLA, and that comes 7.26 square into 27.45. So, that comes your 1446.8 watt, and supply line current after compensation, I mean it comes like, because this power will be divided by 2, so PLA divided by 3 Vs at the angle. So, it comes like typically similarly for all 3, and putting the value, I mean this we get 2.01 ampere similarly for all 3 except the angle 0 degree minus 120 or plus 120, and 3 phase DC STATCOM current we can find out load current minus the supply current, and keeping the value it comes 5.69 at the angle of 45 degree ampere. Similarly, for CB, I mean keeping the value, so it comes typically order of 2.01 and CC it also comes to 2.01 at the angle of minus 60 degree. Well, the load neutral current on DC STATCOM neutral current, that is ILN equal to ICN. So, sum of the 3 compensator current, that comes 7.26 at the angle of 146. So, that is the compensator current which is equivalent to load neutral current, and the V rating of the DC STATCOM will be sum of all 3 phases plus the neutral current lag of 4. So, voltage multiplied the all, and then it comes 4.06 kVA, and equivalent per phase resistance equivalent star connected load is Re 3V square by PLA. So, 3 phase voltage square divided by the power, it comes 119.03 ampere. So, a single phase load, I mean it relies as a balance load at a unity power factor on the supply side through, I mean in this example with the proper design and control. Coming to the 8th example, a 3 phase 4 wire unbalanced non isolated star connected load of ZA equal to 7.0 plus J 90 per unit, ZB 9.0 plus J 2.5 per unit, and ZC 9.5 3.5 J 3.5 per unit has a input line voltage of 415 volt 50 hertz and AC supply and base impedance of 9.15 ohms per phase. It should be realized as a balanced unity power factor load on the 3 phase supply system using 4 lag voltage source based DC STATCOM. Calculate the supply line current, then DC STATCOM current, neutral current, and kVA rating and equivalent per phase of the compensated load. So, this is the typically we have a 4 wire unbalanced load, and we are using 4 lag voltage source converter which typically provide neutral current compensation and load balancing and unity power factor on the load, and after the proper design and the control we have 3 phase voltage, 3 phase supply current which are at unity power factor and balance current, sinusoidal current, and A phase don't typically have a typically neutral current on the supply side is made 0, and these are the 3 neutral current along with the neutral current of the load, and these are the 3 phase current of the typically of the compensator, and this is typically the DC link voltage which maintain 700 volt like. Coming to the solution of this, given that the supply voltage of 415 volt and frequency of 50 hertz, a 3 phase 4 wire unbalanced non isolated star connected load with the impedance of Z equal to 7.0 plus J 9 per unit, and ZB 9.0 plus J 2.5 per unit, and ZC 9.5 plus J 3.5 per unit with a base impedance of 9.15 ohms per phase. So, we can calculate the actual impedances by multiplying the base impedance to these per unit. So, it comes Z equal to this, ZB equal to ZC equal to, and from this we can find out the admittances 1 upon Y equal to 1 upon ZA, ZB and ZC, and now we can find out the load current VA YA. This is the typical per phase voltage multiplied the admittance, it comes 2.295 at the angle of minus 52.515 degree ampere. Similarly, for B phase or load current, if you put the value, so it comes like a 2.809 at the angle of minus 135.45 degree ampere. Similarly, for load C current, we can find out that also comes after putting the value 2.586 at the angle of 99.77 degree ampere. Well, from this load current we can find out the total active power from the voltage and the conductance of the phase, all three phase voltage from this relation, and it comes after putting the value 1567.75 watt. Now, this power is certainly now after the load balancing, it distributed to all three phase. So, per phase power is now 1567.75 by 3, that comes 522.559 watt, and three phase source current are now you can find out I s equal to P upon V s, I mean at the degree. So, this is a per phase power and this is a per phase voltage. So, it comes 20 typically to 2.18 at the 0 degree ampere. Similarly, for B phase will be at the typically at minus 120 degree, and C phase will be again plus 120 degree ampere. So, all three phase will be balanced current, any phase with the supply voltage, and three phase STATCOM current, I mean from the basic relation of current Kirchhoff's law. So, ICA will be ILA minus ISA, and if giving the value it comes 1.9696 at the angle of minus 113.7 degree ampere. Similarly, ICC, that is for second phase of the STATCOM, putting the value it comes 0.9155 at the angle of minus 174.82, and similarly for C compensator lag. So, that putting the value it comes 0.0927 at the angle of 45.42 degree ampere, and the load neutral current will be equal to the compensator neutral current, and that will be the sum of all three phase load current comes 1.606 at the angle of 50.17 degree. The kV rating of STATCOM will be voltage multiplied the all four current. So, it comes 1.2987 kVA, and equivalent resistance per phase will be from the power. We have per phase voltage, we have a per phase after compensation of the current 239.6 divided by 2.18, that comes 109.908 ohms per phase. So, coming to the another example of typically example number 9, a three phase AC supply has a line voltage of 415 volt 50 hertz and a feeder source impedance of 1 ohm resistance and 3 ohm inductive reactance per phase, after which a balanced delta connected load of 21 ohm per phase is connected as shown. Calculate the voltage drop across the source impedance, the voltage across the load in each case, and pendulum volt. If pendulum based STATCOM is used to maintain the voltage equal to the input voltage, that is 415 volt, calculate the kV rating of the STATCOM and the line current. So, that is voltage regulation problem across even resistive load, and the drop is because of the source impedance. So, this is a typical example. This is a typically balanced load, but we have a source impedance, and the STATCOM is responsible to provide the reactive power. So, that this voltage is equal to the source voltage, and we have a 0 voltage regulation. So, after designing properly, these are the you can call it the typically the source voltage, and we have a typically the source current, then we have a load current and compensator current, and the typically the point of common coupling voltage which is regulated to the same as the source voltage, and we have a DC link voltage regulated with the help of both the PI control as we discussed already earlier. So, coming to the solution, given supply voltage of 415 volt at 50 hertz after the feeder source impedance of 1 ohm and 3 ohm 1 ohm resistance and 3 ohm inductive reactance per phase, after which a balanced delta connected load ZLD connect 20 ohm per phase is connected, and we have to convert per phase equivalent to that. So, equivalent load impedance in star connection will be ZLD by 3. So, that will be 21 by 3. So, it comes 7 ohm per phase, and the total impedance in star connection will be source impedance plus this load impedance. So, it comes like your if we add it, that is 7 ampere 7 ohm plus 1 of source, so 8 plus J3, and that comes the impedance of total circuit. So, load current before compensation will be V upon Z. So, this will be the current, and the voltage drop across this current multiplied the source impedance is typically 88.68, and the voltage across the load will be this current multiplied the impedance of the load. So, it comes 199.28 volt per phase in place of your 239.6 volt, and line current that is multiplied by 3 will be 339.96 in place of 415 volt. So, the active power consumed by the load after the compensation is because voltage across the load is now V square by ZI. So, this comes like your typically 239 square or 415 square, because root 3 will be divided by the your load impedance, that is 7 ohm. So, this will be your power 24.603 kilowatt. Now, coming the active power consumed load per phase, we can take it V square typically. So, it will be 1/3 of that. So, it will be 8201.19 watt, and the reactive power of consumed by the load after compensation it is 0. I mean like because we do not have BLD, so voltage rating of the D STATCOM will be Vs equal to VL, that is the voltage rating of D STATCOM 239.6, and the VA rating of D STATCOM will be typically Q minus QL. So, Q can be calculated from quadratic equation for voltage regulation, AQ square plus BQ plus C equal to 0, where I mean this derivation is already given earlier. So, Q equal to B plus minus 1 to B square minus 4AC divided by 2A, where A defines in terms of RS square source impedance and B coefficient 2V square XS and C coefficient VL square plus RS P the power plus XS square P square minus VSC square VL square. So, putting the value of all, we get typically I mean Q equal to here minus 5595.32 VA, and Q D STATCOM will be QL minus QL and QL is 0. So, D STATCOM rating will be the same as typically your 5595.32 VAR like, and divide by 3 will be the per phase kVA. So, total kVA rating will be 3 times this. So, this will be 16.78 kVA and the current rating of the STATCOM will be 3 divided by, so it comes to 23.35 ampere. So, this I mean provide the 0 voltage regulation across the load. Coming to another example 10, a 3-phase AC supply has a line voltage of 415 at 50 hertz and feeder impedance is of 1 ohm resistance and 9 ohm inductive reactance per phase, after which a single phase load having a 15 ohm plus J12 ohm is connected between two lines. If the 3-phase pendulum D STATCOM is used to balance and to regulate the voltage to the same as the input voltage of 415, calculate the supply line current, D STATCOM line current, kVA rating of D STATCOM, the voltage drop across the source impedance and equivalent resistance per phase of the compensated load. So, this is the typical circuit that we have a only the line to line connected, you can call it lagging power factor load, and we have a 3-phase D STATCOM. So, very purpose of D STATCOM is typically to have a balancing of the load across the all the 3 lines, and moreover to provide the same voltage across the load what is the source voltage. So, voltage regulation and typically the load balancing is the task in this case. So, after proper designing you will find 3-phase voltage and 3-phase source current. These are the 2 load current, third load current is 0 because it is connected line to line, and we have then 3-phase compensator current and followed by the DC link. But since it is a load balancing, you will find the second harmonic on the DC link voltage. I mean that will get reflected into the on the DC link because of load balancing. So, coming to the solution, given that the supply line voltage is VAB equal to 415 at the angle of 30 degree, that is the line, and frequency of 50 hertz with the feeder impedance of 1 ohm per resistance and 9 ohm inductive reactance, after which the single phase load of typically 15.J12 is connected between the 2 lines, and we can find out the load impedance YLB 1 upon JB with this. So, this is a load admittance, and for another I mean typically YLB is not connected, it is 0, and for YLC is also 0. So, we can find out like now the load current typically before the compensation, that will be your ILAB equal to minus ILBA, because current is coming from is only line to line connected load. So, load impedance plus the both line source impedance, and putting the value that we get the typically here current 12.03 at the angle of minus 30.46 ampere. The load current after the compensation will be typically I mean equal to the VL upon ZB. So, this current will be 21.6 at the angle of 8.65 ampere. So, all these loads have a rated voltage after the compensation as D STATCOM is connected in parallel to the load, and we can find out the power of the typically the load V square into the your conductance of the AB line, BC line and CA line, and that is because load is only connected across it. So, it will be current through this RL. So, we have a current in this and multiplied the resistance. So, this is the power 998.4 watt, and per phase active power will be divided by these 3. So, it will be 233.2.8 watt, and the reactive power required by the load will be typically of pi square this. So, that is 21.6 square multiplied the 12, that is the reactance of the load. So, it comes 5598.72 VAR. Now, coming to the per phase reactive power, I mean from that it comes like 18.642 for VAR. The per phase required reactance I mean for regulating the voltage QV at this unit power factor load of P equal to this in single phase line diagram. for voltage regulation, VL equal to Vs and QV equal to Q minus QL. So, Q can be calculated from this quadratic equation AQ square plus BQ plus C for voltage regulation, 0 voltage regulation, and keeping this all parameters of the system and the load power with the RS and P and VL this. So, we can find out ABC constant, and then Q comes like minus 733.76, and then total Q we can find out 3 times of this, that is minus 2201 VAR, and we can find out QV equal to QT minus QL. So, keeping this value, it comes like not only voltage regulation, but it has to feed the reactive power of the load. So, it comes minus 2600.15 VAR per phase reactive power for the voltage regulation into the source, and we can find out the typically the current Q upon VL. So, that comes 733.76 divided by 239.6, and that comes current like 3.06 ampere of typically of the STATCOM. So, the supply line current after compensation has a resistive component because load active power and reactive current IV for the voltage regulation to compensate the voltage drop of the source impedance. So, we can have a current now, we can find out this is the current for active power, this is the current for reactive power, and keeping the value we can typically put the value here, and we can get this current typically 10.21 at the angle of 17.45 ampere. Similarly, for B line and C line. So, all balance typically will be the balance current, but at different angle, and 3 phase the STATCOM current will be the load current minus this source current, and it comes for A phase 13.22 ampere. Similarly, for B it will be like a 23.626 at the angle of 145.27 ampere, and similarly for C phase of the compensator after putting value, so it comes 10.21 at the angle of minus 42.55 ampere. D STATCOM V rating will be the sum of all 3 currents absolute multiplied the phase voltage, it comes 11.19 kVA, and the voltage drop across the source impedance will be equal to that current multiplied the typically the source impedance. So, we can find out current and this. So, it comes 92.424 volt, and equivalent per phase resistance in delta connected equivalent will be R equal to 3 V square by power, and that is the voltage and this is the power. So, it comes 73.828 ohm. Coming to another example, example 11, a 3 phase AC supply has a line voltage of 415 at 50 hertz and a feeder impedance of 1 ohm resistance and 3 ohm inductive reactance per phase, after which an unbalanced isolated star configured load is connected, ZL equal to 10 ohm, ZLB 20 ohm and ZLC 40 ohm is connected as shown in figure. And if 3 legs below voltage source based D STATCOM is used to balance and to maintain the voltage equal to the input voltage, then calculate the STATCOM line current, kV rating of the STATCOM, voltage drop across the source impedance and equivalent resistance of the compensated load. So, this is the typical circuit that we have a source impedance and we have a load here, and we have this compensator which is supposed to balance the load and regulate the voltage across the load equal to the supply voltage. So, voltage regulation and load balancing is the typically the very purpose of putting the STATCOM. So, after proper design and putting proper control, these are the voltage typically at the point of common coupling, and these are the current flowing into the line, and these are the typically load current, these are the compensator current, and this is the typically the DC link voltage line. So, coming to the typically solution part, numerical part of this. So, given a supply voltage of 15 volt, frequency of 50 hertz and feeder impedance on 1 ohm and resistance of 3 ohm inductive reactance per phase, after which 3 phase 3 wire unbalanced isolated star connected load with the ZA 10 ohm, ZB 20 ohm and ZC 40 ohm is connected, and load impedance in star connection this is there, and load impedance we can calculate 1 upon ZLA. So, these are the virtually the conductance of the load, and you can find out the load in equivalent to delta connected. We can apply the for this equivalent star to delta connection, and these are the typically equivalent delta connected substance, and load phase current we can find out from now what is multiplied the conductance. So, this comes for line AB, and for the load this comes for line BC and line CA. These are the 3 phase load current, and total active power now we can find out taking V square into the conductance of line AB, BC and CA. So, it comes 8611.25 watt, and per phase active power will be by 3. So, it will be divided by 3, it will be 2870.42 watt, and per phase required reactive power at this for voltage regulation at this UPF load P equal to 2870.42 per phase, a single phase line diagram of star equivalent load, that will be VL equal to Vs for voltage regulation, and where QV is equal to Q of minus the QL, and the Q can be calculated from this quadratic equation relation which we derive, A square Q square plus BQ plus C, where the ABC constant are defined here, and calculating the ABC constant. So, we can get the Q and minus the QL, we will get the for voltage regulation. Since Q is 0 for load, so it comes like a 1240.609, and it comes 1240.669 VAR, and per phase reactive current for the voltage regulation it comes from this QV upon VL. So, it comes 1240.69 divided by 239. So, it comes like 5.18 ampere, and supply line current after the compensation have a resistive component because of the load active power and reactive power for the voltage regulation to compensate the voltage drop. So, we have a typically line current from load active power, and this is the compensator reactive power. So, keeping the value of all, so it comes like a typically if you get it comes 13.05 ampere at the 23.38 degree. Similarly, for B phase and C phase, and 3 phase D STATCOM current we can find out load current minus the typically the compensator current and source current, and from this we can find out typically the current from 4.4 CA 4.03 at the angle of 30.729 degree, and similarly for your B phase it comes to typically 9.71 at the angle of 155.69. Similarly, for C phase it comes equivalent to 5.790 at the angle of minus 19.4 degree at ampere, and VA rating of the STATCOM will be voltage per phase multiplied the current of all three absolute value. So, it comes typically 4701.91, that is 4.702 kVA, and voltage of across the source impedance will be, because we know the typically the current and we know the impedance. So, we can this is the voltage 41.27 volt, and equivalent delta connector resistive load will be from the active power 3 V square by PLT, and that will be 315 square into 8611.25. So, that comes 60 ohm. Well, coming to another example of 3 phase 4 wire, a 3 phase AC supply has a line voltage of 415 volt at 50 hertz, and the feeder impedance of 1 ohm resistance and 3 ohm inductive reactance, after which a single phase load of 8 ohm plus J6 ohm is connected between line to neutral terminal. A pendulum based 4 leg D STATCOM is used to balance and to regulate the voltage same as the input voltage, to calculate the supply line current in D STATCOM and the kVA rating of the D STATCOM and voltage up across the. So, we have a source impedance, we have a load here line to neutral. So, we are connecting 4 leg voltage this voltage source converter, but D STATCOM the very purpose is to compensate the load neutral current and to balance the current and regulate the voltage across the load the same as the supply voltage. And after proper design and proper control and making a model of this, these are the 3 phase supply voltage which is equal to load voltage, and this is the supply current, and neutral current is made 0 on the supply side. This is the typically the load current, only one phase, other 2 phase have a 0, and these are the compensator 4 leg currents, and this is the DC link voltage. Since it is a unbalancing, so second harmonics will be there on the DC link of the D STATCOM. So, coming with the numerical part of the solution, given that Vs equal to 415 50 hertz and unbalanced isolated neutral and star connected load having ZL equal to 8.J6 ohm and ZLB 0 and ZLC also 0, with the feeder source impedance 1 ohm and 3 ohm inductive reactance. We can find out the load admittance for other 2 phase 0. So, we can find out the load current which come 23.96 at the angle of minus 36.87 flowing between the line A phase to neutral, and other 2 are 0, and the STATCOM is connected in shunt with the load. So, we can find out the power active power of the load ILA square IRLA. So, this is the active power of the load reactive, and we can find out reactive power of the load from inductive part, and per phase power if we really have a load balancing. So, per phase power will be by 3 of it. So, it comes 1530.884 watt, and per phase required reactive power for voltage regulation at unit power. So, will be your P equal to 1530.8 watt per phase for the voltage regulation, L equal to Vs. So, QV will be Q into QL, and Q can be calculated from this quadratic equation, putting the value of all and the power respective in this. So, we get the Q equal to 588.39, and the total Q will be for voltage regulation and load balance load compensation. So, that will be equal to typically this by 3, so it will be 17.36.55 VR per phase, and the reactive current for voltage regulation will be total Q divided by VL, and we have a 588.39 per phase divided by 239.6, so compensator current 2.456 ampere, and supply line current after compensation have a resistive component because of load active power and reactive component for the voltage regulation. So, we can find out the active part of source current and reactive power for voltage regulation, and from this we get the value of 6.845 at the angle of 21.017, and for other two phases will be the same magnitude, but at the 120 degree phase shift from one to another and then another also. So, that is typically the neutral compensation, load balancing and voltage regulation across the load, and the 3 phase compensator current will be load current minus the source current, and keeping the value we can get the compensator A phase current, B phase current and C phase current, and neutral current will be just equal to load neutral current, that is a phase current exactly, and this will be 23.96 ampere. The QV rating will be all for 3 line and neutral, and it will comes 14.084 kVA, and the voltage drop across the source impedance will be the current of the source multiplied the source impedance. So, we got already the source impedance earlier, I multiply the source impedance, it comes 21.646 volt. Like coming to another example of 13 number, a 3 phase supply has a line voltage of 450 Hz, a feeder source impedance of 1 ohm resistance and 3 ohm inductance per phase, after which a unbalanced non isolated star connected load is connected with the Z equal to 10 ohm, Z B equal to 20 ohm and Z C equal to 30 ohm is connected between line and neutral terminal and as shown in figure, and if the 4 lag PLOM based D-STATCOM is used to balance and maintain the load is equal to the input 415, then calculate the line supply line current of D-STATCOM and its kVA rating and voltage drop across the source impedance. So, this is typically you can see the load here which is connected unbalanced load here with the different impedance, and we have a 4 wire D-STATCOM which provide the load balancing, the voltage regulation and neutral current compensation, all 3. So, after designing properly and making a model of this, these are the waveform of 3 phase voltage of source which is equal to load voltage. These are the typically source current, balance current and typically balance and cycle current. These are the neutral current of the source which is made 0 after compensation. These are the 4 lag currents of the compensator, and then this is the DC link voltage. Since it is typically you can see the even the you will have it typically here unbalanced load, so second harmonics get reflected on the DC link of D-STATCOM. So, coming to numerical part of this solution, so given supply phase voltage 415 by root 3 to 39.6 volt and frequency of supply 50 Hz and unbalanced non-load star non-isolated neutral and star connected load with ZA 10 ohm, ZLB 20 ohm, ZLC 30 ohm with a feeder source impedance of 1 ohm resistance and 3 ohm reactance per phase. So, we can find out load conductance 1 upon Z by these 3 phases, and we can find out the load current from these respective value. So, these comes the 3 load current for A phase and then B phase and C phase, these are the load current, and the D-STATCOM is connected in shunt with the load terminal. So, load active power can be calculated from voltage square conductance of all 3 phase loads, that comes typically 10,005 to 9.81 watt, and the per phase power will be by 3 of it. So, this is 3508.27 watt, and per phase required reactive power for this load for given power, and same as load voltage equal to source voltage for voltage regulation Q minus QL. So, this is the voltage regulation, this is the load power. So, we can find out typically from this quadratic equation the typically Q required for voltage regulation. We are putting the value of all these elements and solving this, we get typically Q equal to 1601.2 K, and putting the Q minus QL. So, QL is 0 here, so it comes the same as 1601.2 VR, and per phase reactive power from this for voltage regulation can I equal to QV by VL, and we know Q and divide by voltage. So, we can find out the typically 6.6828 ampere, and supply line current after compensation have a resistive component because of the load and reactive component before the voltage regulation to compensate the drop in source impedance. So, this is the active part, this is reactive part which is for voltage regulation, and keeping the value of this substituting this of ISA, ISB and ISC typically comes about 16.09 at the angle of 24.53, all 3 will be balanced. So, it is minus at the 120 degree minus and then 240 minus from A phase, and the 3 phase D STATCOM current can be formed load current and supply current. Putting the value, then you get A phase D STATCOM current 11.46 at the angle of minus 35.64 ampere, and for B phase and for C phase, and then neutral current D STATCOM will be ILN equal to minus CN, and ILN will be sum of the 3 load current, and keeping the value you get the neutral current 14.398 at the angle of typically minus 13.89 ampere, and VA rating of D STATCOM will be voltage multiplied absolute sum of the current, so it comes at 10.181 ampere, and voltage drop across the source impedance will be your typically the current multiplied the source impedance. Putting the value, it comes 50.89 volt. So, these are typically the voltage regulation problem which really in kind of substation. So, coming to a very interesting example, this example number 14, a D STATCOM with a 660 volt battery at the DC side of the VSC is connected to an isolated 3 phase 3 wire 415 75 kVA DG set diesel engine generating system as shown in figure, and DG set is controlled in such that the load on the DC system always remain between 80 to 100% to improve the efficiency of diesel generator system, and there is a load threading provision if the load increases above 125%. If the load is below 80%, the battery charging take place, and if the load is beyond 100%, discharging of the battery take place, and in between 80 to 100% of the load, the battery remains in floating condition. Calculate the whatever rating of the battery and the current rating of the battery and the load on backup of 4 hour is desired. So, moreover calculate the kVA rating of D STATCOM, voltage rating of D STATCOM, and current rating of D STATCOM if maximum load is 125% of active power, 125% of 75 kilowatt of DG set at 0.8 lagging power factor. So, we have a DG set isolated which have a certainly the source impedance, and we are putting D STATCOM along with the battery on the DC link energy storage, and we have a load here varying load. So, the very purpose of D STATCOM with battery is to provide the load labeling on the DG set. So, that DG set is never loaded less than 80% and it is never loaded up to more than 100%, even the load is 120% here. So, that battery takes the energy and give the back like, and these are of course the typically making a develop of complete model. These are typically you can call it the voltage at the across the load, then the typically generator current, and these are typically load current which is unbalanced current, load is also unbalanced load, and these are the of course the 3 compensator current, and typically terminal voltage which is regulated, and these are the power different power when load is varying because 2 phase load is there, then power battery, power of generator on which are varying. So, coming to the solution for this question, giving that D STATCOM with a 60 volt battery at the DC side of the VSC is connected to isolated 3 phase 3 wire 415 volt 75 kVA diesel generating set, and the whatever rating of the battery at full load with the backup 4 hours, equal to percentage of full load into pH. So, it is a 0.25 into 75 into 4, it comes 75 kVA since the battery is required to feed 25% of the full load of active power, and the battery current will be E upon V into H. So, from this we can find out the battery current 28.41 ampere, and active power through D STATCOM will be 25% of the full load, that is 18.75 kilowatt, and PT of 75 into 1.25. So, that is 93.75 kilowatt, and the reactive power of D STATCOM required for corresponding to reactive power of the total power generated. So, that is for that kilowatt, and the power factor of typically 0.8, how much will be the reactive. So, that comes to 70.1225 kVA, and kVA rating of D STATCOM from P and Q we can find out that comes around 72.6696 kVA, and voltage rating of D STATCOM is 415, is connected across line, and the current rating of D STATCOM will be your S divided by 3 VT, so it comes 101.24 volt like. So, coming to another example, a 3 phase self excited 400 volt 22 kilowatt 50 Hz 6 volt delta connected squirrel cage induction generator needs an excitation of 9.238 kVR at no load and 15.257 kVR at unity power factor full load as shown in the figure. P11 base D STATCOM is used to meet the reactive power requirement of this induction generator considering a fixed capacitor rating equal to the no load excitation kVR. Calculate the kVR rating of the D STATCOM, line current, no load at no load and unity power factor load of 22 kilowatt and 0.8 lagging power factor of load of full load of 22 kilowatt and 0.8 leading power factor 20 kilowatt. A fixed capacitor bank is used to reduce the voltage rating of D-STATCOM, and the D-STATCOM is used only for smooth control of voltage at rated value. Then the calculate the reduced rating of D-STATCOM and its line current at different conditions. So, this is the typical system that we have a generator and we have a D-STATCOM here. The very purpose of D-STATCOM is typically providing here the reactive power and along with the capacitor connected here like So, these are the typical waveform after the making the model and simulation, and where the terminal voltage as well as DC link and all the currents are given. Coming to the solution, so given that 3-phase self-accelerated 400 volt 22 kilowatt 50 hertz 6 pole delta connector squirrel cage induction needs excitation of 9.38 at no load and 15.57 kVR at unity power factor full load. For the first case, considering the fixed capacitor bank equal to no load, so the no load excitation Q is a 9.78 which is given from capacitor, and at no load the kVR rating of the D-STATCOM will be Q equal to QC, that is 0 kVR. It does not support to give any kVR, and current rating will be equal to 0. For unity power factor full load, kVR rating is QFL minus QC. So, we have here the load reactive power minus the your generator, that is capacitor 1, and this we get the 6.19 kVR, and line current for D-STATCOM will be Q1 to, so it will be 8.93. So, for 0.8 lagging power factor load of 22 kilowatt, the kVR rating of QST equal to QFL plus Q load minus QC. So, putting the value it comes 22.69 kVR, and the line current corresponding to that calculating it comes 32.75 ampere, and for a load for a 0.8 leading power factor full load of 22 kilowatt comes the kVR rating QST equal to QFL plus QL minus QC. So, putting the value it comes minus 10.31 kVR, and the negative sign denotes the D-STATCOM had to provide the lagging reactive power to maintain unity power factor. So, line current of D-STATCOM will be your IC equal to QST upon by root 3 Vs. So, it comes like a 14.88 ampere. So, in a reduced rating D-STATCOM based voltage regulator, as a D-STATCOM can work in leading or lagging reactive power modes depending upon the extent of load, and its rating can be reduced by using the appropriate rating of AC capacitor at the induction generator ML to cover the total range of the operation. And in most of the cases it is half the required rating other than no load can be selected at the rating of D-STATCOM, and at full load reactive power rating is selected at the rating of AC capacitor. At no load the D-STATCOM will work as an inductor, and at full load it will work as a capacitor. So, for unity power factor load of 22 kilowatt, kV rating of D-STATCOM will be QFL minus Q0 by total by 2. So, 15 this. So, this is the kV rating of D-STATCOM, because at no load it will work in inductive, and at full load it will become capacitive. So, it will compensate on both the side. So, we can find out the typically the capacitor rating from this. So, this comes the typically capacitor rating at no load, and the D-STATCOM is to provide this much kVR lagging reactive power at no load, and at full load it provides the 3 point this leading reactive power. So, line current of D-STATCOM will be Q upon root 3 VL. So, this will be 4.467 ampere, and for a 0.8 lagging power factor load of 22 kilowatt. So, this kV rating will be of corresponding to generator at full load, load kV rating at full load minus the capacitor rating which is we have selected. So, this is the kVR rating of corresponding to the D-STATCOM, and the capacitor rating will be corresponding to accordingly calculated. So, this will be the capacitor rating and at no load, and D-STATCOM is to provide 11.345 kVR lagging reactive power at no load, and at full load D-STATCOM is to provide 11 leading reactive power. And line current for D-STATCOM will be corresponding to putting the value to 16.37 ampere, and for leading power factor at full load the kV rating of D-STATCOM will be keeping the Q minus this corresponding to half. If we put the this will be 5.15, and the D-STATCOM rating of this kVR is required with leading load, and the kV rating will be corresponding to putting the value it will be 4.225 kVR. So, therefore, at no load the D-STATCOM is to provide 5.155 kVR leading reactive power, and at full load can provide the this lagging. So, line current of D-STATCOM IST equal to root 3 this will be 5 typically of 7.44 ampere. So, to summarize this D-STATCOM, we have covered that D-STATCOM offer best retrofit solution for all current based power quality problem, including the like a single phase system, 3-phase supply system, or 3-phase 4-wire supply system, or DG set, which we have given example later on. And PWM voltage source converter are preferred because of the compared to the current source converter to realize these STATCOM because of low cost, reduced size, light in weight, reduced losses because of that, and these are the some of the references, and we like to conclude this STATCOM. Thank you.